All right, so now let's add acid. So we're adding, mix it up here, and I'm going to do 0.03 moles of strong acid, so which we'll just call hydronium. It doesn't really matter if it's if it was hydrochloric acid, nitric acid, same thing. So the first thing is to be aware of what the stoichiometric reaction is. So when you add this strong acid, hydronium, it's going to react with the strongest available base, which will be the lactate. And because one of the pair, the strong acid, is strong, you can expect that reaction to go to completion, which will give us water and the conjugate acid, lactic acid. And now we can construct our reaction table like we did for the other example. So the first entry is before anything happens. So we've got essentially a 0 molar concentration of the hydronium, and we had 0.5 molar lactate and 0.25 molar lactic acid. So in this example, we actually started with fresh buffer. So can pretend that we had not added the base to this. So that's why these concentrations were the original ones. So the next entry here is going to be after you have added the acid, but before it reacted with anything. So before the reaction. So here we've got our 0.03 moles of the strong acid, 0.5 moles or 0.5 molar of the lactate, because this is a 1 liter solution of this buffer, and 0.25 molar of the lactic acid. So the next column is the change with a complete reaction. Now, if you look at the concentrations, there is way more lactate than hydronium. So you expect all of that to be reacted, so that's going to be a change in concentration of 0.03 molar. The lactate concentration will change by a similar amount. And finally, the lactic acid concentration will increase by that 0.03 molar. And then after the reaction, will simply give us 0 molar hydronium. We will have 0.47 molar lactate and 0.28 molar lactic acid. And now we can use those final amounts as the initial amounts in the equilibrium part of the problem, which is what tells us what the pH is going to be by virtue of telling us how much lactate and lactic acid we've got. So basically the idea is that the hydronium gets completely consumed, converted into lactic acid, which then proceeds to produce a little bit of hydronium by virtue of its reaction with water. So let's do that part. So while the stoichiometric part of this process is different whether you add a base or an acid, the equilibrium part is not. So the equilibrium that kind of tells you what the pH is basically the reaction of the conjugate acid with water to form hydronium. And the conjugate base, lactate. And let's not forget water is liquid. And here, this is going to be a proper old school ice table, where we just import the final values from the stoichiometric part as the initial values here. So we said here this is going to be we have 0.28 molar lactate. Again, we can ignore water. The hydronium we're going to stay as 0 to begin with, and we've got the 0.47 molar lactate concentration. Now, because we have no hydronium, you can expect some forward progress to form some, which means that we will also create a little bit of lactate and at the expense of the lactic acid. So when all is said and done, we've got 0.28 minus X molar lactic acid, X molar hydronium, and 0.470 plus X molar lactate. And from here on in, it's kind of downhill. So you can say the Ka is equal to the hydronium, the equilibrium hydronium concentration times the equilibrium lactate concentration divided by the equilibrium lactic acid concentration. And we can rearrange that. It's a more elegant way that I did it in the slide in the previous example. So the hydronium ion concentration is going to be equal to the product of Ka times the equilibrium lactic acid concentration divided by the equilibrium lactate concentration. This is 1.4 times 10 to the negative 4. Times 0.28 minus X, all divided by 0.47 minus X. And we can say that is it's close enough to 1.4 times 10 to the negative 4 times 0.28 divided by 0.47, and that ends up giving us about 8.3 times 10 to the negative 5, giving us a pH of 4.08. Now the pH went down. Remember, the pH was originally 4.15, so the pH did in fact go down, and which is reasonable because we added an acid to this solution. And don't forget, you could have gotten the exact same result. Let me do it in a different color here. By using the Henderson-Hasselbalch equation. pH is going to be equal to the pKa plus the log of the base concentration divided by the acid concentration. So this is 3.85 plus the log of 0.47 or 0.47, 0.28, which still gives you 4.08. So same thing. So either one, so it works as long as you get these guys right here, then you're fine. And so this is how you calculate the pH of a buffer and how you calculate the pH after something is changed. One last thing I want to do real quick is to show you what the pH change would have been if you added that much acid to pure water. All right, so here's that. So black pen here. So again, if you add 0.03 moles of hydronium to 1 liter pure water. So our pH of the pure water is 7. So if the hydronium concentration, if you added 0.3 moles into 1 liter, you will get 0.03 molar, and that corresponds to a pH of 1.53. And so that is a change of 5.48 units. So it went down by 5.48 units. Now note that with the buffer, it was initially 4.15 and then went down to 4.08. So that is merely a change of 0.07 units versus 5 units again. So this is a suppression of the pH change by many, many orders of magnitude, roughly 5, so somewhere in the order of hundreds of thousands. So again, it changed a little bit, but not by much. All right, so that is buffers.